Okay, so this slide is going to give a quick overview of pressure composition diagram and the idea of ideal versus non-ideal solutions. Okay, so this picture that we have right here is essentially the picture of an ideal solution. Okay, so here we are following Raoult's law. That is the definition of an ideal solution. Okay, so ideal equals follows Raoult's law. Okay, and as a reminder, this is our mathematical representation of Raoult's law, okay, where we have a total pressure of our system that is given by the sum of all the individual partial pressures of the components in your mixture. Okay, in this case, we are just taking a simple binary mixture. Okay, each one of those partial pressures is represented by the mole fraction of that component multiplied by the vapor pressure of the pure component. Okay, so this would be the mole fraction of A times the vapor pressure of the pure component A. The mole fraction of B times the vapor pressure of the pure component B. Okay, so this, if your solution follows this behavior, okay, follows Raoult's law, then you have an ideal solution. If it deviates from this at all, okay, then we have a non-ideal solution. So you can imagine that you can have various degrees of varying from Raoult's law, where maybe it deviates just a little bit and it doesn't affect things too significantly. Okay, we can make an approximation of ideal behavior, but sometimes we get some pretty significant deviations from that ideal behavior, and there are some significant consequences to that. All right, so let's dissect this figure that we have here. Again, now we're dealing with vapor pressure, okay, rather than temperature like we did before. All right, so the higher vapor pressure component is going to be up top. The lower vapor pressure component will be down bottom. Again, this is going to be where we kind of switch the behavior that we had in our temperature composition diagrams. All right, so the top this time, this is going to be our liquid phase, and then our vapor phase will be at the lower pressures. Okay, so this line right here, this blue line, represents the total vapor pressure of the mixture, so that's P total. Okay, green is the vapor pressure of pure B. Okay, and then red is the vapor pressure of pure A. Okay, and then so this would be a representation of an ideal solution where our components A and B in this mixture are following Raoult's law. If we have a solution that deviates from this behavior, okay, then things get kind of interesting. Okay, so first let's talk about what kinds of deviations we can have from Raoult's law. We can either have a positive deviation where we have a higher vapor pressure than expected. Okay, so we will call this situation a positive deviation. Okay, or we could have a negative deviation. Okay, where we have a lower vapor pressure than expected. All right, so again, positive deviation, this leads to a higher vapor pressure than would be expected from our ideal. Okay, so that would then lead to a lower boiling point than expected. Okay, and then for the negative deviation, that would lead to a lower vapor pressure than expected. Okay, and then again, that would lead to a higher boiling point. Okay, so again, we could have different scales of deviation from Raoult's law depending on our mixture. Okay, if you have a solution that deviates very strongly from Raoult's law, though, it can be significant enough that it will be impossible to separate the components completely. Those solutions will end up having maximum or minimum boiling points that correspond to intermediate compositions. Okay, so what we would essentially have would be boiling points that are either higher than either boiling points of the pure components or lower than either boiling point of your pure components. And that leads us to the idea of an azeotrope. Okay, so here's a picture of what it looks like when we have that situation where we have non-ideal solutions that deviate strongly from Raoult's law. Okay, these examples are nitric acid and ethanol. Okay, these are two really common azeotropes that you'll encounter. Okay, this type of behavior, this azeotropic behavior, is common for solutions where you have really strong intermolecular interactions between the two components. Okay, so one example that we could see here with our ethanol and water is that we have really strong hydrogen bonding interactions going on there. Okay, that makes it really difficult to completely separate these two components. Okay, so you can see that we have two different types of azeotropes here. For nitric acid, we have what we call a high boiling azeotrope. Okay, so this is where our maximum boiling point, you can see, is higher than either of the pure components in the mixture, which is different than what we looked at earlier for an ideal solution. Remember, that's where we would have a situation that looked like that. Okay, so very different from what we were talking about before. All right, so the consequence of having a solution that is an azeotropic solution is that, as I said, it can be impossible to separate the two components completely. So what ends up happening is, for the nitric acid example, we could do our distillation procedure to enrich our solution in nitric acid up to this point. Okay, once we reach this high boiling point of our azeotrope, that's the limit to how far we can distill. We cannot distill any further. We cannot get any more enrichment in nitric acid past this point. Okay, so that point for nitric acid, you can see, is where you get a 68% nitric acid solution. Okay, so if you go into the stockroom or go on Aldrich or other chemical catalogs, you'll see that a common percentage of nitric acid that you can purchase is going to be that 68%. Okay, similar with our ethanol solution. Okay, so again, we can't distill ethanol. We can't distill pure ethanol from a dilute solution of ethanol. Okay, we can enrich our solution in ethanol up to 95% ethanol, but then we reach our azeotropic limit. Okay, so this is the endpoint of any kind of regular distillation process. Okay, we can't go past that. So that's why when you go into the stockroom, again, if you go in the solvent cabinet, you'll see, or if you think back to your time in working with solvents in the laboratory, you probably saw some bottles of 95% ethanol sitting around. Okay, and that's why 95% is a common number. Okay, that's the limit of our regular distillation process. All right, that's not to say that you can't ever isolate pure ethanol. You've all probably used or seen something called absolute ethanol. Okay, we just have to use some other tricks to get there. So one of those tricks is to distill at a lower vapor pressure. Okay, you know that if you lower the pressure, that's going to change your vapor pressure of the boiling points of your solution. Okay, that's one trick that we have to isolate some higher concentrations of ethanol. So there's some other options that we can use, but again, if you're just doing a regular distillation under normal conditions, these are going to be the limits for the concentrations that you'll be able to isolate for these solutions. All right, well, I hope that was helpful in giving you an overview of distillation and some differences between ideal and real solutions for multi-component solutions, and I hope that was helpful.